talks. The first talk will be given by Stéphane Trebaol from Institut Foton in Rennes, and he will talk about visible light sources for quantum technologies.
Thank you for the introduction and thank you for the invitation. So today we assist to a very interesting talk related to quantum system and quantum technologies. And for such a system to work, we need some key enabling technologies like cryogenics and photonics devices. And during my talk today, I would like to more particularly speak about which kind of laser we need to develop such technology, and also to push these technologies toward the market. So some quantum technology relies on the manipulation of atoms and ions, as we've seen today. We can mention applications like sensing, networking, computing, or even time and frequency metrology. And to manipulate such atoms and ions, we need a laser for cooling, trapping, and probing. Here I take the example of a strontium lattice clock, where you can see that to manipulate such strontium atoms, we need different wavelengths of lasers and also different performances for such laser. I will take as an example this transition, so which is a clock transition at 698 nanometers, sorry. And to probe such a transition, we need a very narrow laser in the Hertz level. And this is requested to have efficient interaction with the atom. If you use a broader laser, you will have uncoupled light through the transition. This can contribute to increase the noise in the quantum system. And you don't only need a narrow linewidth laser, you also need to stabilize such laser to stay in interaction with the transition. So finally, the line width is not the good observable. It's better to look for the frequency noise of the laser that will give you a full picture of the stability of the laser. And this is what I will show you on these slides, is how to swap from, let's say, the usual representation of the laser, which is the laser spectrum, towards the power spectral density, which is the frequency noise. So here, what I show, it's a Lorentzian line width of a laser, which is just limited by the fundamental noise, which is a spontaneous emission of photons. And this is also called Charlottone line width. And you can see that with such a narrow laser, you can effectively probe efficiently in the clock transition. So if we look on the power spectral density, which is expressed in Hertz square per Hertz, this spontaneous noise, this Charlottone line width, will appear as a white noise with amplitude which is called H0 here. The point is that a laser is always in an environment, and so it will face some perturbation like thermal perturbation or even mechanical perturbation, and this will shake the transition in time. And this fluctuation will appear here in the low frequency, so long-term, let's say, fluctuation, and will increase, in fact, the amplitude of the frequency noise. And so if you integrate in time such fluctuation, you will have a broadened transition that we call the integrated line width that usually show a Gaussian profile, and it's not anymore well coupled in the transition. So what we have to keep in mind is the fact that the laser noise will be one of the main limitations for the performance of a quantum system. And here I consider again the story of atomic clock, and I would like to address what will be the contribution of the noise of the laser to the performances of the atomic clock, and in particular here, the Allen deviation, so the stability of this atomic clock. And what you can see is that the stability will be directly related, in fact, to the amplitude of the noise of the laser. So I will come back on this Allen deviation later on in my talk. So if we can also address a different type of atoms. I just mentioned in the introduction the strontium, but we can also mention rubidium, ytterbium, but there is other candidates for quantum technology. And for such atom, you see here that there is a huge variety of transition to probe. And for each transition, you will have a combo between output power for the laser that is needed, that can range from microwatt to watt, and also a huge range of line widths to address, which can be in the Hertz regime towards a few megahertz. So if we try to draw a wish list for such ultra-narrow laser, we can mention that we need low frequency noise that we can refer to narrow line widths, long-term frequency stability, output power that can range from microwatt to the watt level, also relative intensity noise that have to be quite low, and also we need some device that can be integrated in a quantum system with a quite small footprint, and for this we need fiber output and also quite compact laser. So let's have a look now on which kind of technology we can use for such laser. So on this graph here, I plot the intrinsic line width versus wavelengths. So that covers the visible range and also the telecom wavelengths at 1.5 micron. And so there is different laser technologies that can be used. We can mention first a very compact one, which is based on diode laser, which is distributed feedback laser, that have been first developed at 1.5 micron with megahertz line width, and that progressively spread towards the visible range. And today, since few months, in fact, there is some companies that commercialize some DFB laser also in the blue range. There is also external cavity laser diodes that are well known. In that case, we have still laser diode, but here we have also an external cavity that will allow to narrow the laser. I will come back also on this architecture later on. We can also mention rare earth doped fiber laser. These have been mainly developed in the telecom wavelengths, and we can reach here, you see, some hundred of hertz of intrinsic line width based mainly on erbium. And today there is also some research groups that try to develop such laser in the visible range by taking advantage of the maturity of gallium nitride laser diode for pumping. There is also diode pump solid state laser that reach kilohertz line width, and also an interesting architecture which is based on Brillouin fiber laser that show very impressive performances in the telecom range with millihertz line width, and that's also spreading towards the visible range today. So as you can see, there is still a room here to improvement to reach some Earth level directly in the visible range. And to be complete, I should also mention some frequency conversion procedures that can be used by taking advantage of the nice performances of laser at the telecom wavelengths to reach, through nonlinear conversion, the visible range. So this brings me to the outline of my talk. I would like to present to you today two different laser technologies that can be applied to quantum technologies. So the first one is based on gallium nitride laser diode, and the second one is based on nonlinear optics, which is a Brillouin fiber laser. So to develop single mode gallium nitride laser, it's not so easy, in fact, because what we have on the market till now is only Fabry-Perot laser that present a multimode behavior. So we need to implement some external cavity to improve the performances of such laser diode. And the historical approach is a diffraction grating. Here you have the intrinsic line width versus the wavelengths, and you can see that this technology allowed to address some tens of kilohertz of line width. And this is a technology developed by Toptica, which is well known in the quantum technology community. There will also promising approach based on integrated optics. So quite recent results, you see to 22, 23, and there is more recent results now, but still limited in the megahertz line width, and this is mainly due to the losses of propagation that you have in the photonic integrated circuits, and also the losses that you have in terms of coupling between the passive structure and the gallium nitride laser diode. But this will be improved for sure in the incoming years. We can also mention the approach developed by OE waves that consists still in an external cavity, but here the optical filter is placed by a microcavity, which is a whispering Gary mode microdisc with high Q factor in the range of 10 to 8 and even 10 to 9. And with such configuration, you can reach kilohertz line width. And there is also, as I mentioned now, distributed feedback lasers that are available and that show megahertz line width. And so we develop also an architecture still based on an ECDL, so external cavity laser diode. But here we implement a fiber Bragg grating that allows us to reach a very narrow laser. You see in 10 kilohertz line width in the near UV, and even below 200 hertz here at 450 nanometers. So I will develop a bit more this architecture. So we start in 2020 with this configuration where you have a laser diode, so it's a commercial laser diode here, that is coupled through a fiber where you have a fiber Bragg grating by beam shaping with different lenses. And if we look on the optical spectrum, here I will show you how we reach a single mode operation. So here the laser diode is a Fabry-Perot, so it means that you have thousands of modes and you have to select only one mode in the full spectrum. So I just represent here 3 modes of this Fabry-Perot laser diode. And in green here you see the optical function, the filtering function of the fiber Bragg grating that allow you to select just one mode. And since now you have a mirror here, it means that you have an external cavity between the output facet and this Bragg grating, and this will add a new array function with a higher finesse due to the reflectivity of the Bragg grating. And by nicely tuning this external cavity, you can reach single mode operation with more than 10 milliwatt output power. So this is what you can see here on the optical spectrum. You have the bare laser diode in gray, and once you introduce the self-injection scheme, you see that you can strongly narrow the line width. And so then we try to implement more compact devices to be compatible with butterfly package. Here it's a demonstration where you have butt coupling between the Bragg grating and the gallium nitride laser diode. And more recently, an architecture based again on commercial devices, but by directly writing the FBG at the tip of the fiber, we can maintain a quite compact system. And still in the idea of quantum technology and to target some atomic transition, we also implement some tunability based on temperature variation of the laser diode or even on the Bragg grating, and this allows us to tune the wavelengths of the laser. And we also implement some fine-tuning by playing on the current to be able to implement some frequency locking of the laser onto atomic transition. Okay, but the point here is that if I just show you here an optical spectrum, I cannot claim that my laser is really single mode and low frequency noise. So again, I will jump towards the frequency noise picture. And here, this is what I represent. You have the frequency noise versus the frequency for a 400 nanometer version of the laser. And for comparison, I add also the frequency noise of the Toptica DL Pro laser at 420 nanometer. So first, let's have a look at high frequency here, where you can see we have a plateau. And from this plateau, we can extract the white noise contribution of the laser. And by integrating this noise, we can estimate the intrinsic line width. And you see that we gain 1 order of magnitude respect to a Toptica DL Pro, reaching tens of kilohertz. So if now we have a look at low frequency, again, we will retrieve this fluctuation of this narrow laser. And this, if you integrate the noise, you will retrieve a broadened transition, which is still limited in the range of hundreds of kilohertz. But we can face such noise by implementing some locking scheme. I don't have time to develop, but this can be done. And I would like also to share with you a more recent result that we obtained based not anymore on a Fabry-Perot configuration, but on a DFB laser that have been commercialized by Exalos. So this is still the same scheme, but you will see that since now we start directly with a laser that it is monomode, we can drop the frequency noise at a very low level, and you can see that we can reduce by 40 dB the frequency noise of the laser, and this allows us to reach 170 Hz of line width. So this now have to be implemented in a butterfly package to remove and to reduce, maybe not remove, but reduce the technical noise at low frequency. And the advantage of such architecture is that you can spread it to other wavelengths if you have semiconductor materials that are available, as I show here. And let me come back on the quantum technology application, and here I address in particular chip-scale atomic clock. So the idea of such chip-scale atomic clock is to lock a laser on Doppler field transition, and here it's an example of atomic clock developed by the laboratory FemtoST, where the idea is to probe with a 459 nanometer laser a Doppler field transition from the cesium and to lock the laser on it. And currently, such atomic clock performances are limited due to the frequency noise of the laser that is used to 10 to 13. And by using our technology, what we can expect is to reduce this frequency noise contribution to 8, 10 to 15. In that case, the frequency noise should not be anymore a limitation for the stability of the clock. So I will jump to the second part of my talk and present you another kind of architecture that we can use, which is based on visible light Brillouin fiber laser. So such Brillouin fiber laser have been used already, not in the visible, but at telecom wavelengths, also in the context of quantum technology. Here you have a realization of a Brillouin fiber laser at 1.5 micron, that it is transferred to 78 nanometer for a rubidium clock by using nonlinear conversion. This kind of technology is really interesting because you can narrow the laser, so you can reduce the noise of the pump laser and to get at the end a very narrow transition. Here you see the line width of the pump laser, and at the output from the Brillouin system you get something that it is much narrow. And it's not only narrow laser that you can have, but also powerful laser. You see here a realization where you reach few watts of output power. And from our lab, there is also some commercial devices that have been developed, like the Slimliner here, that propose line widths of millihertz level in the telecom range. There is also promising results that have been demonstrated in microresonator and integrated optics, with also 100 of millihertz line widths and 100 of milliwatt of output power. So definitely, Brillouin laser, in particular Brillouin fiber laser, is interesting technology to combine powerful laser and narrow line width laser. So here I recall how it works. So the idea, in fact, is to have an interaction between a pump wave and an acoustic wave in a fiber that will generate through stimulated Brillouin scattering a gain profile, quite narrow gain profile with a line width of delta nu b at the Stokes frequency, which is shifted from the pump by the frequency of the acoustic wave. So to have a laser, we need also a cavity, and so we will study such stimulated Brillouin scattering in a fiber ring cavity with a perimeter of 2 meters. And since you have a cavity, you have an Airy function, and to reach single mode operation, what you have to fulfill is to have only one mode of the cavity that behave below the Brillouin gain. So if you reach such a configuration, you can expect to have a single mode operation. So to stabilize everything, you have to lock the laser onto one mode of the cavity. And one interesting aspect related to Brillouin laser is the fact that, as I said, the pump laser noise will be weakly transferred to the Brillouin laser. And this is thanks to the acoustic wave damping, because acoustic wave will have a short lifetime, which is in a nanosecond regime. And this means that you cannot transfer to the Stokes signal low or long fluctuation of the pump to the Stokes, because this will be directly damped by the acoustic wave. And moreover, since you are using fiber ring cavity, you can have high Q factor in the range of 10 to 8 or even 10 to 9, and this will also reduce strongly the noise contribution. So I will show you now results obtained at 460 nanometers, so close to the cesium transition. Here again, the frequency noise, first of the pump laser, and I will show you how we can reduce this frequency noise. First, by locking the pump laser on the cavity. Since the cavity is more stable than the laser, you can also get rid of almost 30 dB of noise. And then, by increasing the pump power, you can activate the stimulated Brillouin scattering and reach the lasing threshold. And by this procedure, you can also get rid of almost 30 dB of noise. So in fact, by combining these two effects, you can reduce by 50 dB the noise of the laser and reaching Earth level line width. So if we come back again to the story of the Allen deviation, we can expect to reach close to 10 to 15 in terms of stability for a clock. And we also implement some tunability on such a laser. And here what you see is the Doppler field transition of the cesium at 459, which is probed with such a Brillouin laser. So here it's a cartography of different results obtained based on such Brillouin laser or using fiber cavity, photonic integrated circuit, or micro-rod resonator. So main results have been obtained, as I said, in the telecom range, and by the result that I shown to you today at 460, and we also obtained some results at 532, we fill here the gap in the visible range. So let me come back to my conclusion and to this wish list for ultra-narrow line width laser. So we demonstrate some narrow laser with Hertz to 100 of Hertz line width, but not with high powers yet. It's still moderate power in the range of a few tenths of milliwatt. So here I draw what is the target, which is to reduce the line width and to increase the pump power. So we have to follow this arrow. As I mentioned in the introduction, peaks are not yet fully mature in the wavelength range, due mainly to some propagation losses, but we can expect to have nice improvement in the year to come. And you have here our results that I shown to you. Again, through this wish list, the idea is to have some capacity to integrate and reduce the volume of quantum technologies. So such laser diode architecture can be implemented in very small package based on Butterfly. And the result that I've shown to you, it's already a prototype that is developed with the help of two companies, a French company, Oxius and Silensis. And we plan to be able to commercialize such a device in few months. And in terms of perspective, we need today to develop some amplifiers directly in the visible range, based either on the semiconductor or even rare doped amplifiers to reach higher output, optical output power. And with this, I would like to thank you for your attention.
Thanks for the talk. I have a question which is motivated by some discussion I had last week at PTB, where they have a strontium clock and then changed their diet and saw a systematic shift of the measured frequencies, which they attribute to some asymmetric line shape. And then I started wondering about, so in your talk you also always present the laser line width as something beautifully symmetric. You say it's a Gaussian, it's a Lorentzian. But in the end, you have a control loop that stabilizes the laser. If there's the slightest non-linearity in the error signal, wouldn't that give rise to some asymmetric line? And at the level of hertz, I mean, how can you be sure that your line is symmetric?
I don't know if we can say that the line is symmetric, but still I'm not sure that the line width or the optical spectrum is a good way to think about what is limiting. I think we have to look in the frequency noise probably.
Yeah, but how do you see, that would be my second question.
Okay.
How do you see in your frequency noise spectrum whether the line, the laser line, because in the end, you in order to measure frequency, you would go to half height on the left and the right, and you average, right, for the clock.
Yes.
In order to interrogate your clock. And then if you have a kind of triangular line, then the frequency you find by doing that is not the frequency of transition, but there's a systematic shift. So in your frequency spectrum, I don't see, if you don't have the phase information, how you would distinguish an asymmetric line from a symmetric line.
The point probably is also related to here it's a quite simplistic representation that I use because I just mentioned H0. But in fact, what is more important, I think, it's the way how you implement also the frequency locking scheme. Because this is the noise that you will have at the frequency of the modulation. If you use a Pond-Rayver Hall, for example, setup, this is a noise that you will have at the frequency of modulation that will contribute mainly. And so it's not only H0, but it's the amplitude of the noise that you have at the frequency where you are looking for. So, and also the interrogation time that you will have of your quantum transition. I mean, if you are interrogating the system within the microsecond, so it's probably at 1 megahertz that you have to look. But if it's at 10 microseconds, it's probably below in frequency that you will have to check. So you have to consider all the contribution, I would say. There is an interesting paper that is here, the Nature Com that I mentioned here, where they go behind just the line width performances to address quantum system. But they are more looking also on which species you want to interrogate. And so you can have some you have to integrate, in fact, the noise of a larger frequency range, Fourier frequency range, to really address if the laser will be or not a limitation. So it's not, I think, as simple as just a asymmetric shape. It's more looking for the Fourier frequencies and the species that you want to interrogate. You will see if there is a contribution or not.
Thank you. We have time for one more question, one quick question. There was a question here, no? Or there is one there? Oh, you had one question first, no? Okay.
I just had a simple question. To this H0, you were showing that your fiber cavity beats the optical laser. It's simply the finesse of the cavity, or how do I have to think of it? What do I have to do to push the white noise down?
It depends on which architecture we are discussing about, but effectively, if we speak about the first demonstration based on the laser,
sorry, I meant
this one,
yeah, exactly.
you're fully right.
Yeah.
What we just need to have is to try to improve the finesse of the external cavity.
And you can simply do better with a fiber back grating than any grating can be made, or well, I mean, is there a limitation on the gratings, or could I also just make them better? To make
But in fact, after you will have some trade-off between the output power that you will have and the reflectivity of the mirror. So you have to improve the coupling, because it's not only the reflectivity, this is the strength of the signals that you will really inject in the laser diodes that will contribute. So you can implement some anti-reflective coating on the laser diode, but you also have to work on the coupling efficiency between the Bragg grating and the laser diode. And then effectively you can increase the reflectivity, but it means that you will also have lower output power.
Thank you.
Okay, so in the interest of time, let's move on. Let's thank the speaker again.
Thank you.
And now, last but not least, the last speaker is Nicolas Cerf from Université libre de Bruxelles. And we will switch gear a little bit and go back to theory. He will talk about from matrix permanence to many-photon multimode interferometry.
Thank you. Okay, so let me start by thanking warmly the organizer. I didn't make a long trip to here, but nevertheless, it's very interesting for me to be here. And so I'm afraid I'll be a little off topic here. I won't be talking about atoms or ions, but there will be photons in my talks at least. So I'm going to talk about multi-photon, multimode interferometry and some specific phenomenon which we call anomalous photon bunching. So the general context of our work is a boson sampling. So I guess you all have heard about the fact that the sampling of the output distribution for when you have a bunch of bosons, non-interacting bosons that are processed through a linear interferometer is hard to compute, hard to simulate classically. And this leads to the idea that this may be a way of proving the quantum advantage. So this won't be the topic actually of my talk. My point here is that this is eventually all about quantum interference effects, and that's what my talk will be about. So I'm going to talk about, I'll start with a textbook example, which I guess you all know very well, namely the two-photon interference effect, Hangul model effect. So as you know, if you have two photons that are completely indistinguishable in all ways, and if you send them into a beam splitter, a 50-50 beam splitter, they will behave as waves, and therefore there will be, in principle, perfect destructive interference between the way where they both cross the beam splitter and the way where they are both reflected, which means in practice that you will never see a coincidence, right? So this, okay. Perhaps it doesn't work on the screen actually. Okay, so you will never see any coincidence. So either you will see the two bosons, you will observe the two photons in one output or in the other output. Okay, so this is well known. This means that the coincidence probability will in principle be 0. So a very nice consequence of this, is of the fact that it's an interference phenomenon, is the fact that if you learn some additional information, like if you learn the which path information, and in this case, if you know who is who, so if, for instance, you give different frequencies, different colors to the two photons, or orthogonal polarizations, or if you have any means to distinguish the two photons, then they will simply behave as balls, here as classical balls, and each photon will either be reflected or transmitted, and therefore, in principle, again, ideally, this is what you will have. So you will have one-fourth probability for each of the possibilities. So you will sometimes observe coincidences. Okay? Basically, they will behave as particles. And as you also know very well, if you go to the interesting regime in between, so if we consider the photons that are partially distinguishable, like for instance, we could play with the time, so we could make them slightly non-overlapping in terms of time, then you will observe the Hong model dip. So all of this is well known, and the math behind this is also very, very simple. You may actually assign a wave vector to the internal state, as it is called, of each of the two input photons, phi1, phi2, and then the the coincidence probability is a simple function of this overlap, right? So if the overlap is 1, of course, this means that they are perfectly distinguishable, then you will have a 0 coincidence. And on the other extreme case, if they are completely distinguishable, if the overlap is 0, then you will have 1/2 probability. Okay. So all this is well known. That was just my introduction. So what I'm going to talk about is how can we generalize this effect to more interesting, more complex situations. So there are many ways of doing this generalization. One of them is to consider a general interferometer. It is modeled by some arbitrary unitary U, so it's a linear interferometer. And we assume that we send one single photons in each of the input modes. And we are interested in the outcomes where they all emerge into the first output mode, and all the other output modes are empty. So this is very simple to analyze. In that case, you have to compute the probability that you can see here, right? The probability of this overlap, where you have n photons in the first output modes and nothing in the others. And again, this is all very simple to compute. In the two extreme cases, either you consider balls, basically, distinguishable particles, and you simply have a product of the square of the unitaries, which means a product of the probabilities for each of the input photons to emerge into the first output mode. And it's also well known that if you go to the other extreme, ideal bosons, then you get this factorial n enhancement, which is simply due to the bosonic nature of photons. So this probability to a full bunching will be enhanced by a factor n factorial if you consider bosons instead of classical balls. So but the question is, what about partially distinguishable bosons? This was actually studied by Tichy 10 years ago. So he considered the situation where now our input photons, they may have arbitrary internal states. So this could, for instance, be their polarization. This is modeled by the function phi1, phi2, etc. So overall, you have a matrix. This is actually a Gram matrix, which is formed with all overlaps, pairwise overlaps between every pair of two input states. And the probability of full bunching in that case can be expressed. It really resembles the previous expression, but the n factorial is replaced by the permanent of this matrix S, this Gram matrix, which is called the distinguishability matrix. So for those of you who don't know what is a permanent, it's almost the same as a determinant, except that you remove the alternating sign plus or minus depending on the parity of the permutations. They all come with a plus sign. So it looks like a very simple change. Actually, it has very deep consequences, but that's not my point here. My only point here is that we have a permanent, and this permanent can be actually lower and upper bounded. The lower bound will be 1. This would correspond to the classical case where they behave just like classical balls. And the upper bound would be, again, the case of ideal bosons, and where we recover the n factorial term. So nothing very unexpected up to this point. So how can we go even one step further? This was considered by Chechenovic, and that's the setup that I'm going to look at. We will consider a setup where instead of having all photons bunch into one single output mode, we will consider actually them bunching into a small subset of output modes. For instance, just 3 in this example, or 4 output modes. And we are interested in the probability that all photons emerge in this subset of output modes. So in that case, the probability can be written again as a permanent, but this time it's the permanent of the Hadamard product of the 2 matrices, an H matrix and the S distinguishability matrix. The H matrix is defined down there. The H matrix is a matrix you don't need to care so much about how it's defined, but it depends on the interferometer and it depends on the output modes that we consider. So this being known, we have to compute this permanent. So if everything behaves as it was up to now, it's of course very natural to assume that this probability for multimode bunching will be maximum in the case where all photons are all ideal bosons. So in other words, if this S matrix is the matrix filled in with 1, so if when all these states, phi 1, phi 2, phi 3, etc., are all the same. Mathematically, this means that the permanent of this Hadamard product should be upper bounded by the permanent of H. When we take S equal 1, this is the case where each entry is a 1. This is the case where all photons are identical. So I mean, mathematically, you have this inequality, but physically, it simply means that the way we may maximize this probability, bunching probability, will be by considering the ideal case where all bosons, I mean, we have perfect mode matching between all the input modes. So this is actually very plausible. I mean, the main reason to make such a conjecture is that there is an old conjecture in math called, it was done by Bapat and Sunder like 40 years ago, which says that if you want to compute the permanent of the Hadamard product of 2 matrices, 2 positive semi-definite matrices, this upper bounded is given, as you can see here, by the permanent of 1 times the product of diagonal elements of the other. You don't need to care so much about this conjecture. The point is that if you look at our case here, it actually means that this inequality has to be true. So it means indeed that according to this conjecture, it means that the bunching probability should be maximized when all input photons are identical. I mean, another reason it's even more obvious to say that this is plausible is that if you consider one single output mode, I've already shown you that this is the case. The bunching probability is maximum when all bosons at the input are all indistinguishable. Another reason perhaps to believe that this must be true is the analogy with the fermionic case. I mean, in the fermionic case, the inequality gets flipped. The permanents are transformed into determinants, but everything is basically the same otherwise. And there is an analog inequality which was actually proven, I mean, almost a century ago. So for fermions, it goes the other way around, but for fermions, it means that the probability that n fermions bunch into some subset of output modes after being propagated through a linear interferometer is, in this case, minimum for fully indistinguishable fermions. So everything up to now was basically what you could have expected, but actually I wouldn't be talking about this if we hadn't fallen almost by accident on this paper, which is now almost 10 years ago, but which has remained mostly unnoticed in the literature. It's a mathematics paper by Stephen Drury, some journal. It's a very short paper. The abstract is a counterexample to a question by Bapat and Sunder is presented. Basically, it displays a matrix, and there is really no interpretation. And the paper is 1.5 pages long, and basically you cannot really get anything from this paper, except that now we know the conjecture is wrong. So of course, this triggered our curiosity, and we wanted to know whether we could find quantum optics implications of this. And I will skip all details, and I'll immediately jump into the result. So our result is that this particular interferometer with this particular input state will will be an implementation, quantum optics implementation of this counterexample. So here, F5 here is a 5-mode Fourier interferometer. You have 2 beam splitters, 2 theorist beam splitters, just boxes. And we feed this, so it's a 7-mode interferometer. And it so happens that I was saying I had my state phi 1, phi 2, etc. But it so happens that a 2-dimensional Hilbert space is good enough to implement the counterexample, so we can naturally think of polarization. So basically the polarization of my 5-state, phi 1, phi 2, phi 5, up to phi 5 is shown there on the block sphere. You see that you have 5 equally spaced polarization states along the equator, plus the north and south pole, which are these V and H polarized inputs. So the claim is that something weird will happen with this particular interferometer and this particular input polarization pattern. And that's indeed what we noticed. So you can see in the green box there, you can compare the situation where everything is ideal. We send just 7 photons with the same polarization, same wavelength. So the matching is supposedly perfect. In that case, the probability of bunching would be something like 7 10 to the minus 3. And if you now take the same interferometer and send these photons, which are now partly distinguishable, so they look a little more like classical balls, not completely, but they are along the way to becoming classical balls, so to say, the probability of bunching is slightly larger. It's 7.5, 10 to the minus 3, which shows that there is what we call a violation ratio. So first of all, this phenomenon, we call it anomalous. So we call it anomalous bunching. And the violation is something like 7%. So what's nice is that now that we have a quantum optical implementation, we can think as physicists. So we can, of course, immediately generalize it. First of all, instead of a 5-mode interferometer, we can take an N-mode interferometer, and just everything is almost the same. And what's interesting is that in that case, I should also say that the input polarization pattern should become this time an N-branch, what we call a star-shaped. Okay, so this block sphere that you have seen before, instead of 5 states along the equator, we will have N states along the equator, still the north and south pole. And now we see that the violation ratio, it scales as N. So we can actually get a very large violation. You should keep in mind that both the numerator and denominator term, they actually decay exponentially with N. So I don't claim that it's easy to measure this ratio because both numerator and denominators are very small. So they, for N large, they will not be experimentally accessible. But nevertheless, theoretically, we know that this ratio will increase as N. So another interesting thing, I won't have time to explain it in all details, of course, but the thing is that now instead of just observing this violation, we may try to understand where does it come from, because we can understand it as an interferometer. And let me just give you a very short clue about how it works. So here, I consider here as a benchmark the ideal case, where I have single photons all occupying the same polarization state, entering this interferometer. And the main point is that at this intermediate step here, I could show it here. Actually, we have here, the state that we have here is a known state. I mean, this was actually known. So this means that it will be a superposition of N photons in the first or N photons in the second mode. And if you propagate it and you would like all photons to end up in either the first detector or the second detector, it's immediate to see that there will be an N+1 factorial entering the formula. And if you compare it with the situation, the setup that interests us, the setup where we input this polarization pattern, then the state which I've indicated there with crosses, this will be another state which will, I mean, at least we know its dominant term will be N photon Fock state simply, but occupying a mode which will be actually a superposition of the different polarization and spatial modes. So that will be the leading term. And this is actually easy to understand that because of the Angles-Mandel effect, there will be an N+2 factorial entering the formula instead of an N+1 factorial. So by looking at this circuit and knowing quantum optics, it's very easy to understand why we get this violation. So we have kind of an explanation of this behind this violation. When here you can simply see that the violation is, we have in yellow here, we have a lower bound to the ratio, to the violation ratio R. And you see that the blue curve is actually the exact values. We may compute the permanent up to around 20, because computing a permanent is becoming extremely exponentially long. But you can see that we need to have at least 7 photons with this particular setup to observe a violation. With 6 photons, it would not work. We have no explanation for this, but I mean, that's a fact with this particular setup. So how much time do I have left?
10 minutes, 9 minutes.
Okay. Okay, so let me show you here what we call the landscape of distinguishability matrices. Here I'm considering now a ternary mixture of the distinguishability matrix corresponding to distinguishable particles. So this is this point, so just classical balls. This is the distinguishable matrix of ideal bosons, and this is this star state that we have found. So what in colors here, what you see is the value of the log, actually, of the violation ratio. So, of course, the ratio is 1 here, the log is 0, and it decreases nicely because we know that the bunching probability decrease when we go to distinguishable bosons. But what you can see here is that the behavior between this and this point is that it goes down and then it goes up again. So in some sense, you could say that this anomalous bunching setup, which we have found, is kind of an isolated island. So it means that if you remain in the neighborhood of ideal bosons, what I mean by the ideal bosons is bosons where polarization, time, frequency, everything is exactly the same, so the boson being fully indistinguishable. So you see that in this neighborhood, it looks like the bunching probability will go down and for some reason go up again and go even a little higher for this anomalous bunching example. So this led us to make another weaker conjecture, which we called a local multimode bunching conjecture, which is that even though we now know that the bunching may be slightly higher, 7% higher somewhere else in this landscape of distinguishability matrices, at least in the neighborhood of the ideal case. So when I consider all same input states with an epsilon perturbation, at least in that case, the probability of bunching should go down, right? So this is what we call the local multimode bunching conjecture, the fact that this probability admits at least a local maximum near the case where the bosons are fully indistinguishable. This looks even more reasonable than the previous conjecture. And again, it's very plausible for many reasons. First of all, you may look at, you may just do the perturbation calculation and look at the first derivative, and it's easy to see that this boson, ideal boson point is a stationary point, which means that at least the first derivative is 0 for all possible perturbations. So if you perturb in any direction, you see that this derivative is given by 0. So that's of course the first step. But obviously we would need to look at second order perturbation to be sure that we have a negative term instead of in front of epsilon square. So we have done it for some simple case where we only perturb the polarization, and we may compute explicitly the probability of bunching as a function of epsilon, the strength of the perturbation, and also depending on V. The vector V is the vector which tells you precisely how do we perturb the polarization. And it so happens that it's very easy to compute the epsilon square term, and it depends on this quantity, which of course we wish to be negative, if it indeed was a maximum, if the local maximum was indeed, if it was true that we had a local maximum. So another way of saying it is that the maximum, this quantity will never be, of course, above the largest eigenvalue of f. So f, I won't spend time on this, but f may be defined. It's some matrix, some positive semi-definite matrix. And of course, if we could prove that its maximum eigenvalue could never exceed the permanent of H, then everything would be good, and at least we would be sure that the ideal bosonic case would be a local maximum. But as you may guess, this is actually another conjecture. There happens to be another conjecture by these two same people. 2 years later, they conjecture that the largest eigenvalue of this matrix F is actually equal to the permanent of A being an arbitrary positive semi-definite Hermitian matrix. So again, you don't need really to look at all the details, but this means that if this local multimode bunching conjecture was true, it should be the case that this would actually be a proof of this Bapat-Sunder conjecture, second conjecture. So conversely, if this second conjecture was wrong, then the local multimode bunching conjecture would be wrong, and this is what happens. Funnily enough, the same guy, Stéphane Trebaol, also found a counterexample 2 years later. This is a little bigger. This time it's a complex valued matrix. Again, there is no explanation behind this, but at least there is a matrix here, which is such that if you compare the largest eigenvalue of this matrix F with the permanent of A, there is indeed, I mean, this time it's small, it's just not even 2%, but there is a little excess. So we know that this conjecture is wrong. And we may, of course, as you may guess, we may also translate it into something interesting from a quantum optics perspective. So this time the scheme is a little more complex, but we can do it, and we actually exploit the eigenvector corresponding to this eigenvalue which is exceeding the permanent of H, the one which is violating the conjecture. So I won't spend much time on this. Let me just show you here that indeed we have a violation ratio. So this point here would be ideal bosons, perfectly indistinguishable. And you see that by perturbing it slightly here, we may increase the probability of bunching locally this time. We have photons which are almost indistinguishable. So it can go up, and at some point it goes down again. And we have indeed a positive coefficient here in front of the epsilon square term. So we have anomalous two-mode bunching with even nearly indistinguishable photons. Just before concluding, let me just say that this would never happen for single-mode bunching. Single-mode bunching, the trick is that we do not have there the permanent of an Hadamard product, but it factorizes. We have a dependence on the distinguishability matrix on the one hand and a dependence on the interferometer on the other hand. These two dependencies are factorized. Therefore, we know for a fact that the single mode output bunching probability can only go down. This is how it looks like for the same scheme. So you see that in this same scheme, if you look at the single mode bunching probability, it goes down, and it can only go down. So all this to say that anomalous bunching can only happen if you consider at least two-mode bunching or more. I mean, we don't know, but we should probably also work for more than two modes, but not for one mode. So let me conclude here. So this is just the beginning. There are plenty of open questions that we can't answer. I mean, first of all, what are the other counterexamples? There most clearly must be other counterexamples, even possibly simpler schemes. We don't know if this scheme with 7 photons in a 7-mode interferometer is the smallest scheme that we could think of in order to demonstrate this violation. So this is not known. We don't know whether a stronger violation could be observed in an accessible, hopefully experimentally accessible scheme. So we also would like to know what could be the applications for this, for instance, in the validation of boson sampling experiments. And more generally, there have been plenty of conjectures on permanence. Permanence are poorly understood in mathematics, and therefore, I mean, it's quite interesting to investigate a bit further this interplay between linear algebra and, in particular, the permanence of matrices on the one hand and multi-photon interferometry on the other hand. So these are the 2 papers that we have written on this topic, and I forgot to mention my collaborators from the beginning. So here you have Benoît Seron, Leonardo Novo, who co-authored with me the first paper where we found out this phenomenon. And then a second paper with a PhD student of mine, Leo Pioche, who was actually here, but he has left. He didn't want to listen to me, apparently. And he actually has a poster. I don't know if you've seen it, but he has a poster about this. Thank you very much.
Thank you. We are a little bit out of time, but maybe we have time for one quick question.
Thanks for the talk. When it comes to indistinguishability, one can, of course, look at the a priori indistinguishability of the photons looking at the scalar product as
Yes.
you did. but there's also the question if the detector can distinguish the photons, and you didn't talk about that at all, but in principle, if I have two photons with different center frequencies and the detector is fast enough, I still see a modulation of the coincidence probability in time, right?
Yes.
So can you maybe even maximize the violation of some conjectures by playing with the bandwidth of the detector in addition?
Most probably you're right. Actually, this is something that I would like to investigate. I mean, I didn't say it, but here at the moment, we always assume that on the measurement side, this measurement here, it actually does not care at all about what we call the internal degree of freedom, which in my example was polarization, but could very well be frequency or time. So indeed, there has to be some duality. I think there should be a kind of a dual where I don't know exactly how to answer the questions, but it's clear that there has to be something of this type. So, I mean, you're right, but I don't know really how to elaborate on this at the moment.
Okay, well, thank you very much. Let's thank the speaker again. And this concludes the session, and I guess the conference. And maybe, Takao, you have some concluding words, no?
Okay, well, time flies. Yes, as we come to the end of this conference, I'd like to express my sincere gratitude to all the invited speakers, poster presenters, and participants for contributing to such an inspiring day. And this conference has also underscored the importance of the collaboration between Europe and Japan in advancing quantum science and technologies. I'm very confident that the connection we made and the ideas we exchanged during this conference will lead to new collaborative projects, for example, JST Aspire projects, and also to deeper long-term partnerships. And before closing, I'd like to thank all those who made this conference possible. In particular, Jean-Louis Mogat for his exceptional leadership and coordination. And Patrick Bitte-Philippe for his indispensable advice and support. And Saori Fukuyama and Ayami Sugimoto. And also Midori Onoda, who is still working in Japan, for managing extremely complicated logistics, which has become even more complicated because of the national strike. So this conference simply would not have been possible without their dedication and hard work. And finally, I'd like to thank all of you once again for participating this conference and making it so wonderful and fruitful. So thank you very much, and I wish you all a pleasant evening and also a safe trip back home. Thank you very much, and ありがとうございました。
So we would like really to thank you, Professor Aoki, for having been the power and the brain of this, really successful event. So it was very successful in terms of scientific substance, but also in terms of number of participants. So 78 participants, so this is really great. So thank you very much for this once again. It was also very successful due to, well, the high number of young researchers, as President Gemma underlined it this morning. So we would say that what the future of our EU-Japan collaboration is secure. So thank you very much. And so in the name of our two universities, we would like to thank very much, very warmly, the Japanese mission to the EU, and of course, in particular, Ambassador Aikawa, for their constant and very strong support to Waseda Brussels office, but also to our two universities. Thank you once again to Brias. Thank you, of course, huge thank you to the Waseda Brussels office for, well, the amazing job you did, Jean-Louis, of course, Patrick, and Guylaine, and also, of course, Frédéric Pognard. And last word to say that together with Vice President Gemma, we intend, of course, to continue collaborating together. And so, well, we hope to see you next year for the 8th conference, which will also give us the opportunity to celebrate the 10th anniversary of the Waseda Brussels office. So we wish you a safe journey back home. Kyo tsu kete. Arigato gozaimasu. And now, well, let's drink. Nomi masho.